Welcome to this lecture where we will give an introduction to Internet ossification. What causes the problem and what are some possible ways to deal with it? My name is Anna Brunström, professor in computer science at Karlstad University in Sweden. So in the lecture we will start with looking at the original design principles for the Internet. Then how has the Internet changed over time and what are the underlying causes for Internet ossification? We will look at some ways to overcome the ossification problem and finally a summary of the lecture. So let's start by taking a look at the original design principles behind the Internet. So the original goal was to develop an effective technique for multiplex utilization of the existing interconnected networks. And the design to handle this problem was the packet-switched architecture and IP. And within this original design, there was a strict layering of protocols, where each protocol layer provided a service to the protocols above. And this allowed each layer to be developed independently, and you could just focus on different solutions at a particular layer, and then you would have a structured way of interacting with the layers below and above. And in this original architecture, we have a single protocol at the network level, the so-called thin waist in the IP hourglass model that we see to the right in the slide here. So you have IP in the middle as a single protocol, and this means that you can have a multitude of services on top of this. So you could have TCP, UDP, other protocols, and on top of that, various applications. Similarly, underneath IP, you can have a variety of different networks. And as long as these networks support the IP protocol, the hosts on those networks can communicate with each other in a peer-to-peer fashion. So if I know your IP address and my network supports IP, then I can communicate with you. Original design of the Internet was also built on the end-to-end principle, where the main responsibility for the communication was placed in the end systems. So the end systems were smart and the network was dumb. There was no real state in the network, rather only some soft state perhaps, but you could not make any assumptions about the communication that was going through the network. You just forwarded the IP packets and the intelligence was in the end nodes. So these were the underlying principles of the original design of the Internet. What has then happened to the Internet architecture over time? Well, the first is the success of TCP. So TCP is today the most commonly used transport protocol over the Internet. And it has basically removed all the other protocols from operation. And this means that the transport evolution has been very slow. And when you have a very successful protocol and most applications use this protocol, well, then the network can start to make assumptions about the underlying traffic. We'll also see in the success of the socket API. So this API is used by most of the network applications over the Internet, and it provides a mapping from the application down to a transport protocol. And in most cases, that transport protocol is TCP. We have also seen a great success of the web. So today, most applications actually communicate over HTTP, over TLS, over TCP. And when you have such a successful protocol stack, the rest of the architecture starts to ossify around this protocol stack. And we have seen also emergence of a lot of different middle boxes that have then made assumptions about the traffic that runs on top of the network. So today our network is far from stateless. We have a lot of middle boxes that manipulates the traffic in different ways. So you may, for instance, have firewalls to provide security. You have network address translation to deal with the shortage of IPv4 addresses. You have various performance enhancing proxies and things that may accelerate your TCP communication or that tries to optimize your web transport. And all these success factors and the large fraction of middle boxes has contributed to the Internet ossification, where it today is very difficult to introduce a new protocol over the internet or to change anything inside the network. So our IP hourglass that we saw on the previous slide has changed its shape. And today, basically, we have a waste that consists of HTTP, TLS, TCP over IPv4 or IPv6. And on top of that, you have the applications, and below you have the link technologies. But it's very hard to change any of the protocols inside this ossified network architecture. And this, of course, causes a problem for innovation and for introducing new solutions that better can support our future services. So what are some examples of the internet ossification if we look back at the original design principles that we looked at? So in the original design, we had a strict layering of protocols. Today, of course, the network may inspect, rewrite, or insert higher layer data into the communication. So it may look at the traffic to treat various flows in different ways. Your net gateways will rewrite your IP addresses or port numbers. And you may also have more invasive changes, for instance, by content rewriting for performing compression of images over a wireless network or manipulating the content for security. In the original internet architecture, the thin waist of IP should enable the support of many different types of communication services above. But today, it's very difficult to send anything but TCP and also UDP possibly across the network. So if you try to send some other protocol, this packet has a large probability of getting dropped in the network. In the original design, the end-to-end principle said that we had smart end hosts and dumb networks. So there was no state in the network. This, of course, is very different today, where we have this magnitude of middle boxes that keep a lot of state and that expect to be able to track entire connections and see all the content, for instance, of a TCP connection. We also had a thin waist where any host that was connected and knew the IP address of the other side would be able to communicate with each other in a peer-to-peer fashion. This is again not typically possible today because of firewalls and the network address translators. They have enforced a directionality of the communication where today it's the client typically has to initiate the communication, and then once this is done, your server can respond to you. And this has brought us to the client-server architecture that we see for most communication over the internet today. So what are then some ways we can try to deal with the internet ossification? Well, one way is to try and extend the services that do work. So TCP is working over the network, so we can perhaps extend TCP to provide additional services. And a prominent example of this is multipath TCP. But extending TCP is not very easy, and the design of multipath TCP has been heavily influenced by the problem of making the protocol work through middle boxes. So multipath TCP uses multiple TCP subflows for its communication, and each of these subflows has to look like a regular TCP connection to make it through the network. And there has been a lot of effort to make sure that the TCP options that are used in multipath TCP is designed in a way that they work even if you have middle boxes that may rewrite the initial sequence number of the TCP flows, or you have middle boxes that may copy unknown TCP options between segments, for instance. Another method is to try and build on top of the transports that do work. So to encapsulate your protocol on top of TCP or UDP. And the prominent example here is the QUIC protocol. So the QUIC protocol that is currently under development within the Internet Engineering Task Force is built on top of UDP. So the functionality of QUIC is built on top of UDP, and this means that it can get through the network and it's not seen as a new protocol. And the content of QUIC is also encrypted in order for the network to not be able to ossify around its content or to manipulate the content of the packets. If we are trying to communicate between two peers in the network, it is, as I mentioned, difficult to set up that connection due to the presence of network address translators and firewalls. So in order to support such communication, we have several techniques that have been developed that are providing signaling to try and facilitate the traversal of such middle boxes. So here we, for instance, have the ICE, stun, and turn protocols that have been used for peer-to-peer media communication. So ICE, the Interactive Connectivity Establishment, will try to find a way to set up a connection between the two peers, and it may use stun, session traversal utilities for NAT, or turn, traversal using relay NAT, to facilitate this communication. So in the example on the figure in the slide, we first see an example of two peers, both having private IP addresses behind the NAT that needs to communicate with each other. And this can be facilitated by having the communication go through a relay server, such as is the case for turn. Another way to try and help deal with internet ossification is methods to discover the end-to-end capabilities so that you can determine if something works over the network. Because if you don't know what middle boxes you have to traverse or what is supported on the other end of the communication, then the only way to find out is to try it out. And this is, for instance, used in the happy eyeballs mechanism, which has been introduced to allow the deployment of IPv6 to make progress. So here you try to set up a connection over IPv6, but you also have a fallback where you, after some time delay, also try a connection over IPv4. And then whatever connection completes first will be used for the communication. And this method allows you to try IPv6 as a preferred communication method without introducing the full delay of having to wait for a complete timeout if this doesn't function. Rather, with some time delay, you can try IPv4 immediately. And finally, to try and overcome the ossification from the socket API, we can also try to have some more expressive APIs. And this is the approach taken by the Transport Services Architecture, TAPS, which is currently under standardization within IETF. And within the TAPS architecture, it also tries to facilitate some of these other mechanisms so that you provide a more flexible API for the applications that run on top, and you also provide some of the other services that is needed to combat ossification. So the transport system can provide you with a fallback between different protocols, for instance. To summarize, we have seen in this lecture how the internet architecture has ossified over time due to the success of TCP and the web and the assumptions that the various middle boxes in the network has made about the communication that runs on top of them. So today we are in a situation where it's very hard to introduce new protocols on the internet. We have seen that there are different solutions that can be proposed to deal with this problem, where we can try and build on the protocols that do work, TCP or UDP, and design solutions on top of it. We have various protocols that tries to help set up communication between two peers and deal with the fact that they may be behind different network address translators. And we have seen that the strict and limited services available by the socket API also contributes to the internet ossification. And the TAPS architecture, the Transport Services Architecture, which offers a new, more flexible service-based API, is one way to try and solve this problem. And in the coming lectures, we will look in more details at this TAPS architecture and the concept of transport services.